my name is Luvarous Johnson, and today we'll be looking at the ultrasound machine. Okay, we're going to look at how to calibrate and how to do some of the simple troubleshoots for this particular device. So here we are in a medical setting, and behind me we have here a standard portable ultrasound machine. We'll go ahead, and one of the main things that we're going to look at today is not necessarily the entire system itself, because most of it is just computer, but we're actually going to look at the most important part of the device, which are the transducers. These transducers are what you use to go ahead and actually do the scanning using ultrasounds on patients. Okay, basically, well, first of all, what we'll describe is what is an ultrasound. Ultrasound are sounds that are above the frequencies that can be heard by the human ear, anything above 20 kilohertz. In this case, for diagnostic ultrasounds, these machines produce sounds and frequencies in ranges of 1.6 to 10 megahertz. So it's far greater than what the human ear can hear. First off, what we're going to look at is basically how do we go ahead and calibrate these transducers. That's what most of the calibrations have to deal with when we go ahead and look at the ultrasound machine. Really, like I said, we really don't do any calibrations with the machine or the transducer itself. First off, let's look at the composition of the transducer. Now, I can't take this transducer apart. We can go ahead and try to give you a visual of what's inside this transducer. Basically, behind this faceplate right here, see here, there's what we call a piezoelectric material. This particular material, mostly ceramic, is a type of material that when we induce voltage across the material, either expands or contracts based on whether that current is positive or negative. It's a DC current. When that happens, it converts that electrical energy into sound energy. Same type of technology used in sonar when dealing with, say, submarines underwater. Okay. The reason we do that is because sound travels through mediums such as water or the fluids in the human body, and when they hit solid objects, some of that sound is echoed. It's kind of how sonar works, and in this case, this is how we produce an image with these transducers. So a ultrasound wave is emitted across the piezoelectric material, travels through the human body to a certain depth, maybe hitting bone, or in this case, I'll say we're examining, say, a gallbladder. Upon striking that gallbladder, some of that sound is echoed, returned to the transducer, so it also works as a receiver. That analog data that's received by the piezoelectric material is then converted into digital data, sent back to the computer, and that's how we get an image on screen. Okay? So in terms of calibrating these transducers, what we use is a water bath. And at the time we're calibrating these transducers, they're not even hooked up to the ultrasound unit right here. We actually disconnect the probe, we connect it to a synthesizer and an amplifier, because we're going to produce our own voltage across the transducer to create an ultrasonic wave of sound. So when we do that, what we first have is, unfortunately we don't have it here today, but we have a water bath. It's basically a tank filled with water. On the sides of the walls of the tank, we actually have acoustic absorbers, because we don't want any of the sound reverberating back. Basically, I'll explain why. We're going to go ahead and have this transducer in a fixed position down into that water bath. Across from it, approximately 250 millimeters, we're going to have what's called a hydrophone. Hydrophone is a device that actually captures sound and converts it back into voltage so we can get a reading. Okay, with this hydrophone, we'll go ahead and have that hydrophone across from the transducer, and any sound that actually passes that hydrophone, we don't want to reverberate off of the walls of the water bath and come back across the hydrophone, because then we'll get an improper reading. So we want any sound that passes it to be absorbed. Okay, so we're going to set that transducer down into the water. We're going to apply a voltage across it, voltage that we know will give us a certain level of produce a certain sound wave, a certain frequency of sound wave. We're going to set the synthesizer to emit a wave that's stepping up, starting at 4 millihertz. 4 millihertz of frequency, all the way up to 9 millihertz of frequency. For every burst, the sound emitted is in burst tones, as we call them. For every burst tone, it's going to step up 0.1 millihertz, all the way until it reaches 9 megahertz. I'm sorry, 0.1 megahertz, all the way until it reaches 9 megahertz of sound being emitted. So with that, we'll go ahead and run that test. All of that data that goes across the hydrophone will be fed into a computer system that we have connected to the hydrophone with technology, with software that's designed to go ahead and read the voltage level and make sure that we're getting the right amount of return energy, I guess you would say, that sound energy being converted back into electrical energy, that we're getting the right amount received. That will show us that our transducer's working right. Okay? If we don't get the right readouts, then we know that our transducers are not working right. Basically, that's the calibration for the ultrasound machine as in a whole. We basically just test each one of these transducers to make sure that they're working right. Now, we're going to look at troubleshooting. What if these transducers are not working right? There's a couple of things that could be happening. Okay? In terms of troubleshooting, we could have, with these transducers, as a biomedical engineer, you want to look at a few things. You want to make sure that there's no swelling around this front lens, because this is where the sound is emitted from. It basically works like a kilometer, the same that we see in X-ray and in CT. It focuses the beam of sound. Everything on the side is made with an acoustic absorbing material, so on the inside, so there's no sound escaping outside of that window that you're trying to examine, or the ultrasound technician is trying to examine. Okay, so you want to make sure there's no swelling, no cracks. Make sure that this head is not detaching from the base, because that can be a problem. What occurs a lot of times too is when the head is attaching, you actually get moisture down in there. It can create an electrical hazard for the patient and for yourself. Okay, so you want to make sure that none of that is occurring. Okay, one of the main problems that a lot of ultrasound techs run into is the fact that they're not getting a good image produced. Okay, now that could be a number of reasons too. One of the first ones, when you first meet with that ultrasound tech, you want to ask them a few questions and you want to check a few things. We're going to go ahead and get a closer look here. In 1 second. Okay, here we go. And we're going to look at the ultrasound machine right now. And I'm sorry, I'm going to get off that image. Now, when we're here in this mode, we can see the screen, right? And our transducer's connected. So I'm going to set the transducer back here in its holder. I'm sorry, give you a good look here. Give me 1 second. Okay, the transducer's back over here in its holder. And you can see on screen that there's a number of settings there that the ultrasound technician can choose from. Now, what happens sometimes, and this is just a simple mistake, but sometimes you might not see nothing on that screen. And why is that? Basically, they have no options. They can't choose anything. I'm sorry. And they're wondering why. Basically, you want to ask them first, do they have the transducer from its port locked in? When you basically go down here, you'll see that it's not actually locked. It's unlocked. And it can easily be removed from its base. When that transducer is not locked, the system automatically goes into a freeze mode and doesn't give the ultrasound user, the ultrasound technician, any options. So what you want to do is you want to go ahead and lock that. See, now it's in lock position. If we turn it back, we'll open it. We come back up and check. And once again, our options are available. I don't know if you can see that very well, but basically our options are available. So this is just a computer system here that the ultrasound technician goes ahead and uses to select various settings for what they're scanning, if they want to do 3D or 2D. Okay. Now another problem is, say they have that, but they're not getting a clear image on screen when they go ahead and scan. One of the problems with that can be, and what happens with a lot of transducers, is that some of the elements break. We were talking about piezoelectric material earlier. That piezoelectric material is actually multiple pieces of ceramic that's known as elements. Okay, if even up to 2 of those elements are broken, they get a distorted picture on screen. Basically, when those elements are broken, you're not getting a complete sound wave produced. So there's holes in it. At that point, basically the transducer will either have to be repaired or just have to be replaced based on the damage. Another thing that we want to make sure of is that if those elements are fine and we're not getting a clear image, we want to go back down here to our base. And this goes to our IT days. Let's go and look here, I'm sorry. Where the base of the transducer locks in, if you look here, you'll notice we have pins. Basically, if you remember IT, got a few pins here. It's what's known as a pin grid array or PGA connection. Okay, some of these are actually LGA as well. Okay. So if they're LGA, you want to make sure that they're not dirty, that they're getting a complete connection. If they're pin grid array, PGA, you want to make sure that none of the pins are bent. Basically, if some of the pins are bent, you're not getting the full connection, meaning you're not getting the full voltage across the transducer. And when that happens, basically, you won't get the right amount of frequency being produced across a piezoelectric material, so you won't get a very, very clear image. Also, the material, the data being returned, all of them might not be collected because some of the pins are damaged. So you want to go ahead and check that. One of the last troubleshoots that we want to look at that occurs is that sometimes the user says that the system is locking up, everything freezes, and they don't know why. You want to go ahead and tell them to shut down the system and then go ahead and start it back up. If it still freezes, that basically just means that you have a corruption in the software. So as a biomedical engineer, you have to go ahead and get the software for that particular unit and go ahead and reinstall just like you would do on a computer. Basically, you have to do a complete system reinstall, and then go ahead and it should work fine with that. Okay. So I'm sorry if the view wasn't so great. I'll give you a last view of the ultrasound machine. We'll go here, have a few controls, a trackball, works just like a computer and a mouse, transducer, okay, and also I just want to say one last thing too. Sometimes these transducers get damaged or get water damage based on the gel being used on the transducers. Here we have MediChoice, which is a good one. Sometimes, unfortunately, some medical facilities buy gels that are cheap. They kind of destroy the transducers, they mess up the heads. So you want to make sure that they're not using something that's not, I guess you would say certified to be used on it. Make sure the clean materials they're using are the right ones, not something that might damage the transducer because it is made out of rubber, plastic. So you want to make sure that they're doing that. And if they are, you want to go ahead and replace it and make sure that they don't use it anymore, okay? So besides that, that's all there is to pretty much ultrasound. It's calibration and it's troubleshoots. So at this time, we're going to go ahead and say goodbye. If you got any questions, ask the guy that's sitting in the class who looks just like me. Thank you.